With all the source and destination possibilities under CAPI Snap, we define 4 basic paradigms that show how your data can flow. The first paradigm is the offload engine. In this mode, your source and destination are both host memory. The application calls the action, and the Snap infrastructure sends the data to the accelerator. The action performs the function, and then Snap returns the data to the specified destination. In both cases, the source and destination come from host memory. The next 2 paradigms, the egress and ingress engines, transform data as it moves into or out of the server. Encryption and decryption might be example use cases for these paradigms, but you can also perform database operations such as search or sort in the ingress model. Here you take advantage of the speed of the FPGA doing sorting, merging, or searching algorithms on the data as it gets pulled into the server. The final paradigm is the funnel engine. In this case, we take advantage of the huge I/O bandwidth on the back of the FPGA card. You can use this when you have many different source locations coming together, or if you need to filter large amounts of data. This mode might be used for streaming video and filtering the incoming images for regions of interest, or formatting the video for cognitive machine vision algorithms.
So hello, my name is Bruno Mesnay, I'm from the CAPI team and working on enablement. So that was a quite good experience, and our first experience porting some application to Snap. One day a sales guy in France asked me to do porting. We had a meeting scheduled with the French customer 3 weeks after, and the customer told us, hey, here's a program, show me what you can do with that on a FPGA. So this customer knew that porting a program on an FPGA in 3 weeks is nearly impossible, or very challenging, I would say.
The customer, having read about CAPI Snap, approached IBM about the viability of a SHA-3 algorithm on a FPGA. The customer had C code of a sponge, or check algorithm, which is a specialized version of a SHA-3 encryption. After receiving the request, our team ported the C code to CAPI Snap in just 3 days. After a mere 11 days, we had a fully optimized version running. We took the results back to a very impressed customer soon after that.
In 2 days we were able to compile it without any big modification in it. And this means that we had a VHDL code. VHDL is the assembler language for FPGA. Then we took a week to optimize, tune things, parameters, to get more and more performance.
We show here an excerpt of the check algorithm in C. The original code, without the yellow highlight box additions, is what we fed into the Snap and Xilinx Viva tool, set at the early stages. The yellow boxes highlight the slight modifications we made for performance by the end of the 11 days. But as you can see, the code snippet remains very readable to a programmer. There were 3 yellow box changes we made. The first was to separate the input buffers from the output buffers, so the FPGA didn't have to write to the same location it was reading. The other 2 changes, for unroll and pipeline, allow the compiler to perform parallel operations on code segments. With unroll, we make parallel instances of a code segment whose result don't affect the next iteration, which is a common case on loops. And the pipeline function allows portion of code to begin an operation before the previous iterations complete. The results were outstanding. In less than 2 weeks, with minimal changes to the original source code, we had the CAPI Snap implementation of the check algorithm running 35 times faster than the processor version. That's not comparing the FPGA to a single thread of processing. We obtained the 35 times speedup compared to 20 cores running a total of 160 threads. This performance improvement was consistent across all sets of parameters we fed into the engines. You'll note that the chart shows two sets of FPGA results, a 16 slice version and a 32 slice version. This is an indication of the number of parallel pipelines we were able to fit into the FPGA. The 16 slice version takes up less space on the FPGA and was quite simple to implement. Getting the 32 slice version to place, route and time was a little more challenging. Of course, if we used a larger FPGA, we could fit even more parallel instances, leading to even higher performance. You'll note how well the model scales from 16 to 32. The performance doubles once the number of elements go beyond 32.
One of our most popular use cases is around a paradigm that we call the funnel engine. In it, we have a large amount of data that's sitting outside the server, and we're going to filter it as it passes into the server and host memory. The POC that we did is called the intersection algorithm. In this POC, we have two unsorted arrays sitting in storage that we're going to pull out, filter, and find the common elements in both arrays on the FPGA, and then store it into host memory. That compares to pulling all the data into the host memory and running the same algorithm in software.
This intersection benchmark was created by Lu Yang, our CAPI lead in China. In database operations, it's quite typical to pull multiple large data sets from storage and then have software perform a filtering operation on the data in order to find the small amount of data that's actually of interest to the query. There are two problems with this operation. First, with the cost of host memory at a premium, you're filling your local storage with data that you aren't interested in. And second, you're pulling large amounts of data across your PCIe link, which can take quite a bit of time for large data sets. By combining the I/O retrieval with the data filtering on the I/O, we hypothesized that you'll gain in three ways. First, the FPGA will perform the filtering much faster than the processor. Second, you'll send less data across the PCIe, saving time. And third, you'll only load host memory with the data that you need. This slide shows the steps in the processor software method of an array intersection operation. We place the array data in the I/O card for this benchmark. For comparison, the time to access the array data from the on-card memory is the same for both cases, software and FPGA. Our software benchmark starts with a host requesting the retrieval of two target data arrays from I/O. The I/O card accesses the arrays, and the full data set is placed in host memory. The software then reads the arrays and performs the intersections before storing the intersection results into host memory. Compare the previous software method to the FPGA intersection process shown here. We still start with the host program kicking off the request to perform the intersection of two arrays that are in the I/O card memory. But rather than sending the data to the host, the FPGA performs the intersection on the card. From there, it stores the results into the same host memory location that the software used, giving the exact same results. For our benchmark, we ran different size arrays and different data intersection hit rates. The different array sizes are shown in the rows on the results table. In green, you see the benchmark results for software,
while the FPGA results are in purple. For both cases, we split the time into two parts: data access time and intersection algorithm time. All times are shown in microseconds. The array access time for software is step 2, and the array access time for the FPGA is step 5, corresponding to the steps in the previous two charts. The intersection algorithm time is step 4 for software and step 3 to 4 for FPGA. Sure enough, the FPGA outperforms the software by 4 times or more. You see that the total time is dominated by the intersection algorithm time, but the data access is consistently less, as we are sending only the results across the PCIe bus in the FPGA case. Note that the resolution number data in both cases is always the same. This indicated that the results data matched in both cases on all rows. This benchmark, along with many other samples, can be found in our CAPI Snap GitHub site under example code.